EE? Yeah, you betcha. Are there any other questions? Okay. All right. So before I do percent EE, I just want to say one thing. So all of the practice exams are all equally good. They all cover the same content. If you don't see the overlap of the content, that means that you're struggling to understand the content. So if you think that these questions are like totally unrelated, try to verbally explain them, like talk them out. Either talk them to a peer, like explaining why the right answer is right, wrong answer is wrong, or to your pet, or to a poster, or to a pillow. Just try to actually verbally speak the explanation. If you struggle, then that's something that you want to come to office hours or ask your TA in recitation about to make sure that you are able to understand the concept. And hopefully then you'll start to see that all of the questions are equally as good. There is one thing that we are not going over, which is from So the spring 21 Dr. Baldwin's exam, question number 9 is asking you to calculate A values. That one we didn't do. So that's the only thing that, like, just skip question 9, calculating A values. All right. But everything else we went over, everything else is equally as good. And for today's practice questions, we're just going to do spring 19 because it was the first one listed. So we'll just go through those practice problems for Dr. Baldwin's exam. And just one other quick reminder. So I have 3 of my previous exams uploaded. The format of the exam is going to be most similar to my summer exam. So that's just where everything's kind of really condensed together. That's just to try to save paper. So your exam format is also going to be kind of more squished to try to save paper. But you will get scrap paper and you will get this exact periodic table. So you will have a periodic table as well. But again, all of the content is equally as good. All right, so let's add a page to do a quick review of EE. So our percent EE is our enantiomeric excess. So that is how much more of one enantiomer do we have beyond that racemate, beyond that 1-to-1 ratio. So that is what the excess is telling us. How much extra of one enantiomer do we have? So to calculate it, it is equal to the percent of the major enantiomer minus the percent of the minor. Or it is also equal to the alpha of the mixture over the alpha of the pure enantiomer times 100. So those are the 2 formulas that you needed to have memorized for the enantiomeric excess. When going between percent EE and ER, the thing to remember is for that enantiomeric ratio, you need to watch out what each enantiomer is being defined as. So if it's the plus to the minus or the minus to the plus, so pay attention to which enantiomer is where in the ratio. And it's going to be where you say that percent of the whatever the one enantiomer is plus that 100 minus that percent is going to be of the racemate, which we can then break down to say, all right, half of that is the major, half of it is the minor, and then you can combine those to get the total of the major. So, for example, calculate the percent EE and ER if your alpha of your mixture is -4, I get, yeah. Yeah, and I just need to pick a bigger number. And the alpha of the pure let's make it a +8. So you have to first figure out, okay, well, which enantiomer is the major? Calculate the percent EE, and then do your enantiomeric ratio. So what's your percent EE? All right, go ahead and talk to people around you and see if you can get the same answers then, and then we'll regroup. Do we have a percent EE yet? Yeah? Okay. What's the percent EE now? 50. Good. Okay. So the thing that may have tripped you up is the fact that I gave you the pure alpha of the other enantiomer, right? Because your major is going to be that negative enantiomer because that's what the alpha of the mixture is closer to, right? Because remember, each enantiomer is the same value, but the opposite direction. So if one of them goes -8, and then the other one goes +8, but then my mixture is there at a -4, then that means that I'm going to have a lot more of the negative enantiomer in order to go that counterclockwise direction. So I'm going to use this formula because I have alphas. So that's the formula that I use to just say, all right, my percent EE is going to be the alpha of the mixture over the alpha of my pure enantiomer times 100. I can't have a negative percent EE, so I'm going to use that -8 as my enantiomer that I need so that it cancels out, so that it is a 50% EE of that negative enantiomer. What is my ER? I think I heard it. 3 to 1, yeah. So to find the ER, it's going to be that 50% negative plus 50% racemate, which means that it is 25% negative plus 25% positive. So then I combine my negatives to get a 75% negative to that 25% positive. Then I just get the simplest ratio of that, which is a 3 to 1 for the negative to the positive. Cool. Any questions about calculating percent EE or ER? Yeah. This one just happens to be negative. If I had given you a positive 4, then the major would be the positive enantiomer. Yeah. So when you're doing ER, then it doesn't matter as long as you specify which one is which, or pay attention to if I give you the, like, normally what I do is I give you a blank line, and I'll be like, negative to positive. So then you got to put the number with the number, or with the correct spot. Cool. But if I don't give that to you, then yeah, you just have to define what the ratio is. Any other questions? Cool. All right. Has anyone attempted this version of this exam yet? Yeah, a couple of you have. Okay, all right. So this first one is just definitions. So we can just go through. The heat absorbed or released during the course of the reaction. So let's see, out of the words that we have. This might be easier if we just tried to define the words. So polarizability is going to be based on the ability to distribute its electron density unevenly. I was pretty sure that was one of the words that was already used, so that way I didn't have to write the definition. So that's the polarizability. It's just the ability to, like, make your electron cloud uneven. So you are just unevenly distributing your electron density. Just like how you can have a dipole moment for a polar bond or a polar molecule, that's the polarizability, the ability to become polar, essentially. Hybridization, that is the mixing of our atomic orbitals. Which actually is F. So that uses hybridization. Conformations is our conformational isomers. So that is if you are rotating a sigma bond, which compounds with identical connectivity but different orientation in space. Do we have the word stereoisomers? Yes, stereoisomers is better fit there. Our conformations or conformational isomers are going to be, actually, I guess conformations is just the way that we draw it, is what it's better defined as when it's just that generic. So we'll say the conformational isomers. That's where you rotate a sigma bond. Our stereoisomers are where you have the same connectivity, but different 3D arrangement. What is it if you have different connectivity? What's that word? Constitutional isomers. It's the fundamental makeup of it is different. So it's a constitutional isomer. So that was the two branches, was either different connectivity, constitutional isomers, they have different IUPAC names, or you have the same connectivity but different three-dimensional arrangement, that was our stereoisomers going down that other side. Or I guess it'd be constitutional was on the left, stereoisomers was on the right. All right, so we use stereoisomers. Conformations didn't currently look like there was a good spot for it. Transannular strain is actually a term that we didn't use. So this is actually the sterics of groups on the same ring, like bumping into each other. So it's kind of an A13 strain is a type of transannular strain. Do we have that? Yeah, here we go. So we used that 1,3 diaxial interaction. Of that steric crowding of two groups across a ring. So transannular, just meaning like it's across your ring. Quantum mechanics is where you are looking at the location, the study of the location of your electrons. So theory of electron motion, it's quantum. So we got that. Gibbs free energy is the energy associated with the, I hate having to define Gibbs free energy. It's like the energy that is gained and lost during a reaction, I guess is a way you could kind of define it. I wouldn't have you do that one because I don't have a good definition for it. Pi bond, that is the overlap of that side-on p orbital. Entropy is disorder. Kinetics is the study of reaction rates, which we got here, is D. Mechanism is the arrows showing the flow of electrons in a reaction. Electronegativity is the ability to attract electron density through a sigma bond, through your bonding orbitals. Resonance is the delocalization of electron density through p orbitals. So it is specifically through the p orbitals is resonance, because we're going to have two other types of delocalization of electron density. Induction also delocalizes our electron density, but it's going to be through sigma bonds. And then we're going to have hyperconjugation, which is going to delocalize electron density through space. So we're going to have additional ones, but the only one that's written here is resonance, so that's the best answer for this question. Torsional strain, that is the repulsion of electrons in eclipsing bonds. Functional groups, these are the groups of repeating patterns of elements in bonds. Octet rule is saying that we need 8 valence electrons. in order to be stable. Coulomb's law, ooh. I haven't thought about that in ages. Yeah, I don't even know. We're gonna get rid of that Gen Chem 2 concept. We got, I hope that's not Gen Chem 1. Yeah, I don't know. Enthalpy. Enthalpy. That's our heat energy. Thermodynamics is the study of reaction energies. So we had our thermodynamic control was if you were getting to the more stable product, the lower in energy product, whereas our kinetic control was going to be based on whichever one formed faster, right? Had lower energy of activation barrier was kinetics, lower product energy was thermodynamics. Steric hindrance is where two groups try to occupy the same space. So our groups are just bumping into each other. Nucleophile is going to be our electron-rich species. It is the Lewis base. Oh, too far. And then electrophile would be our electron deficient species. It would be the Lewis acid. I'm trying to think about some other keywords. Yeah. Any questions about just definitions? Just what the words mean? Yeah. Oh, I didn't even see A. Yeah. Yeah, don't do what I did. Actually answer all the questions. Any other questions? Okay. All right. Answer the questions using your general knowledge. Cool, yeah, just do it. Sweet. All right, circle the molecule that contains a bond formed by the overlap of sp3, sp3 orbitals. All right, so which one is it gonna be? Left or right? Left. So remember sp, our indicator is triple bond. sp3 is our indicator of all single bonds. sp2 was the indicator of double bonds, or if you had a carbocation, or a lone pair of electrons in resonance. So what I'm gonna do is I'm gonna go, all right, I'm gonna find my sp hybridized atoms first. That's what's gonna let me answer the question quickly, is find the unique identifier, sp hybridized orbitals. Don't try to assign all orbitals. That's not what the question's asking. It's asking for the triple bond, single bond overlap. So I'm looking for that sp-sp3 overlap. So I'm like, cool, that's gonna come from one of the neighboring sites. So I just need to look at, all right, what's next door? Next door to the left of the alkyne is sp3, to the right is sp2. So then that bond is my sp3 sp overlap, or sp sp3 overlap. This other one is another sp sp2 overlap. All that's doing is look at the hybridization of the atoms directly next to each other. That's what makes that sigma bond. Any questions about hybridization? Sweet. All right, circle the molecule that contains a lone pair not involved in resonance. So 1, 2, or 3. We'll label this 1, 2, or 3. Yeah. Yeah, it's 1. How did you know? Yeah, so your lone pair is on the double bond. Whereas for all the others, the lone pairs are next to the double bond. So if you're next to the double bond, you're going to have resonance. The difference here is that the lone pair is on the double bond. So that nitrogen has what hybridization? sp2, right? Double bond sp2. How many sp2 hybridized orbitals do you have? 3. 1 plus 2 is 3. So what is my 4th orbital? What didn't get mixed in? A p orbital. So the p orbital is the only way to get that pi bond. That's the only way to make that double bond. Then I look at, okay, each of those sigmas, the sigma of the double bond and the sigma of the single bond, are from those sp2 hybridized orbitals. And then the lone pair goes wherever there is still space. So this lone pair is in an sp2 hybridized orbital. You will not have resonance with hybridized orbitals. Resonance is only through those unhybridized p orbitals, the unmixed normal p orbital. That's the only way to get resonance. So that lone pair is an sp2 hybridized orbital, so it is not in resonance. So another way of asking this question of circle the molecule that contains a lone pair not involved in resonance would say circle the molecule that has a lone pair of electrons not in a p orbital. Actually, then 1 and 2 would still both be right. Let's do 2 to make sure you understand why that's true. All right. For 2, what is the hybridization of that oxygen? sp2. So it looks sp3 because you see two single bonds, but it has lone pairs. Lone pairs say stop, look next door. I have a lone pair next door to an sp2 hybridized atom that says I get resonance. We also already said we have resonance, but the fact that I get resonance means automatically I must be sp2 because you will never, by definition, never have resonance with sp3. So that oxygen must be sp2. So how many sp2 hybridized orbitals do I have? 3. 1 plus 2 is 3, right? We just said that we had 3 sp2s. What's the 4th orbital? P is that unhybridized p orbital. All right, so now when we look at this oxygen atom, because that's what we're trying to assign it for, so my sigma bonds, again, have to come from the hybridized orbitals. So then the lone pairs get whatever's left over. So my lone pairs are in the sp2 and p orbital. So I get resonance with the lone pair of electrons in the p orbital. There is no resonance with the lone pair that's in the sp2 hybridized orbital. So another way of asking this question could have been, how many electrons do you have in unhybridized p orbitals? Or how many electrons are in a pi system? And you would say 4. There would be the 2 from the double bond plus the 2 that are in that p orbital. Right? These are all ways of asking the exact same question of where are your electrons located? Cool? Any questions about that? All right, sweet. The better you get at this will also really help you in Orgo 2 as well. Like that's a skill that'll like keep translating out. All right. Circle the most acidic, oops. Okay. So I wouldn't ask you to do this. Let's instead say, circle the molecule with the most acidic proton. I wouldn't tell you an approximate pKa value, or I would give you both pKa values and then say match them up, in which case the smaller number goes to the more acidic one, the larger number goes to the less acidic one. So I don't expect you to have pKa values memorized. All right, so between them, which one is going to be more acidic, left or right? Left. Oops. So let's expand this out. I get 3 methyl groups all connected to that molecule doesn't exist. What's wrong with this structure? Yeah. Yeah, that carbon has 6 bonds. Yeah, so what this is saying is you get your 3 CH3s all attached to a carbon, that carbon, and then you have to have that be a carboxylic acid. That's a sad, sad carbon. That's way too many bonds. Yeah, there's missing another carbon in there. So what they were trying to do was that. It was missing this carbon, is that carbon. So that structure doesn't exist. I wouldn't try to trick you though, so if you ever look at that, like raise your hand. And especially if you're also, I know that we have quite a few people at the testing center with SLDS exams, you can still ask questions, whether you're at the testing center or SLDS, like they call my cell phone. So if you come across something and you're like, I don't know what this is asking, call me. If you're in the normal testing room, then you just raise your hand. But yeah, you can always ask questions. So if you see this and you're like, what is that? Then that would be something that I would then clarify with the rest of the class and answer your questions. But what I was hoping that you would have seen is that you get that hydrogen on that atom, whereas here, all of these hydrogens are on carbons. So this one's on oxygen, that one's on carbon. So the factor that we are using is atom electronegativity, is what determined that the carboxylic acid is going to be more acidic. That would be the factor. It would be atom electronegativity. We chose atom electronegativity because carbon and oxygen are in the same row, in the same period on the periodic table. Same row, electronegativity, same column, you do size. Okay. Circle the condensed formula for the structure drawn to the left. Ugh, okay. All right, which one is it gonna be? Left or right? It's the right, because of that carbon that was missing on the other one. That's that carbon. So I didn't even look at the rest of it. I didn't look at the right half of it. I looked for this. Ooh, what functional group is this? Ester, good. Actually, let's do all of these. What functional group is this one? This was one you didn't have to have memorized, but if you know it, it could potentially help you as extra credit. Imine. And how about this one? Ether. It's where you get the oxygen with carbon on either side. Cool. So what I saw was the ester. So I looked for that carbon of the ester next to my CH3. That's how I did that quickly. All right. How many unhybridized p orbitals are there in the structure below? What number we get? Yeah. No. We have a lot more than 6. Over 10. Yeah. 13, beautiful. So each double bond is made up of 2 unhybridized p orbitals, that side-on overlap of 2 unhybridized p orbitals. That's how we get that pi bond. So I'm like, cool, 2, there's another 2, there's another 2, there's another 2, there's 4. And then remember, your carbocations exist in the p orbital. So what I did was I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Is how I quickly counted that. Cool. All right, we're going to determine the hybridization of each heteroatom. So heteroatoms are what? Anything that's not carbon or hydrogen. So that means I only have to do it for how many elements on this molecule? 2, the oxygen and the nitrogen. So students usually will waste a lot of time where they're like, oh, trying to assign hybridization for the entire thing. That won't be graded. Actually, it might be graded. You might get minus points for it. So because it depends on if I'm trying to understand, do you know what the word heteroatom means? Then I'd penalize it. If I'm feeling really nice, then I won't penalize it, and I'll just only grade the nitrogen and oxygen. All right, so what is the hybridization of that nitrogen? sp2. It looks sp3, but it has a lone pair, so you stop, and you look next door. Next door, I see that sp2. The other ones are sp3, I don't care. All I gotta do is see one sp2 that immediately tells me I can have resonance, so that nitrogen must be sp2. All right, what is that oxygen? It is sp3. It does not have resonance because it looks sp3, but you stop and say, all right, I look next door is sp3. sp3, there is nowhere for those lone pairs to go, so that oxygen remains sp3. All right, which Newman projection is lowest in energy, the left or the right? The left. So how we know is we're looking for those Gauss interactions. I know I'm doing Gauss because I am staggered, right? Staggered is that Gauss interaction that I'm looking for. That is where you have 2 non-hydrogens that are 60 degrees to each other. It is a type of steric interaction. So I look and I go, all right, there is 2 non-hydrogens. There is 2 non-hydrogens. Here is a non-hydrogen and a hydrogen, so that is not Gauss. Hydrogen, non-hydrogen, not Gauss, because I need 2 non-hydrogens. So that's it. This one has 2 interactions. Then the one on the right has 3 interactions. I would have also given you 2 of exactly the same molecule to not try to make it as tricky, because I would have wanted you just to identify the number of interactions. Cool. Any questions about Newman projections? All right, sweet. All right, we're not going to name all of these. We'll name the last one. I see some people opening up your notes. I understand the urge to do that, but I recommend when you're studying, try to fight that desire. Try not to open up your notes. Try not to look at the answer key. See how far you can get just pulling from your memory, because that is a form of active studying. Don't be afraid of that discomfort, of that struggle. That is learning. Go as far as you truly can with your brain. Convince yourself that you know the right answer. And it's only when you're absolutely stuck that then you would check the answer key, but you can also just wait because I will give you the answer. So if you really are stuck, then it's okay. Like it's not bad that you're relying on notes, but given that the exam is on Wednesday, I would hope that you wouldn't need your notes as much right now, would be the desire. Just try to see how far you can get. Like really just challenge yourself. And if you can't get all of it, it's okay. Just see how far you can get. All right, so right away, we need to be able to identify our backbone. The first thing that I see is that ring. The ring is going to be higher priority. If I had a primary functional group, then I would start at the primary functional group. I don't have a primary functional group, it's all a hydrocarbon, so I start at the ring. The ring is going to be my backbone. So I'm going to use that cyclo prefix. My root is going to be hex for my 6 carbons. And then it's going to be an ane because it's all single bonds. So my backbone is a cyclohexane. All right, now I get 2 substituents. I have a 2-carbon chain. 2 carbons is eth, and then YL tells me substituent. Remember to know all of your roots. It is meth, eth, prop, bute, pent, hex, hept, oct, non, dec. You need to know 1 through 10. Remember, once you get up to 5, it's polygons. So pentagon, hexagon, heptagon, like they all, it's 5 through 10 is, polygons. So the hard ones are meth, eth, prop, bute. 1 through 4 are the ones you really want to focus on. So eth is the 2-carbon chain, so it's ethyl for a substituent. The hard part is that this is now a branched substituent. So my numbering always must come from the true backbone. I must start as close to the true backbone as possible from that cyclohexane, and then I number out. I get a 3-carbon chain, so that becomes a propyl, but I haven't accounted for that 1-carbon substituent coming off of it, so that is a 2-methyl, and that goes in parentheses. So that is a 2-methyl propyl substituent. What is the common name for that substituent? Isobutyl, good. I know it's iso because I see a little Y. The Y is iso. All right, so 2-methyl propyl is the naming convention I would expect you to use. Isobutyl is a common name, so you will not use it on the exam. The instructions will specifically say do not use common names, so isobutyl won't get you credit. You won't be penalized for it, but it won't get you any points. So 2-methyl propyl is the name of that substituent. So now I need to figure out my numbering. I can either number left to right. I want to give the lowest combination numbers, so I want my substituents to have smallest numbers, so I'm going to start at one of the substituents. So I can either go left to right that way, or I can go right to left. To figure out which one I need, I would find the smallest combination. Well, either way, it is a 1 and a 3. That means it is a tie. So I now need to go off of the alphabet as my tiebreaker. So I'm going to compare the E of ethyl to the P of propyl. I'm comparing it for the backbone of the substituents. That's what I'm trying to get at, is comparing those alphabets. So E comes first, so E gets to be number 1. So I'm going to put this together. I get my 1-ethyl hyphen 3 dash close or open parentheses 2-methylpropyl close parentheses cyclohexane. And Dr. Baldwin didn't have this hint, but I will always have it. Use stereochemistry when necessary. Is stereochemistry necessary here? Yes. What is the stereochemistry that I get here? It is cis. You could also use R and S if you wanted to, but cis is easier. Yeah. The isobutyl, A, B, C, D, E. E is always coming before I, so even if you had isobutyl, it would still be lower alphabetically. It is the alphabet is the deciding factor. So it is the smallest combination of numbers. If it's a tie, then the alphabet is our last ditch effort. Yes. So, okay, so technically, I didn't actually teach you this, so I would have accepted either. Because this is a bold line as opposed to an actual wedge, it's not a triangle, it's just like the rectangle bold. Cis actually is the better term here because it's not an absolute assignment. The absolute assignment requires wedges and dashes. I wouldn't have done that. I would have given you an actual wedge or a dash. In which case then, let's practice assigning R and S. If you use cis, I would have accepted it. I also wouldn't have given you a molecule that would have been ambiguous. So there would have only been one appropriate answer. Or I would accept both. All right, so for this, we have hydrogen is, I'm gonna do the right one first just because a little bit more space. Hydrogen's on the dash. So I get, oops, carbon, carbon, carbon. And then I walk out from that. I get 2 hydrogens and a carbon, 2 hydrogens and a carbon, 2 hydrogens and a carbon. And then off this one is 3 hydrogens. This one I get 2 carbons. That one I only get 1 carbon. So that makes this 1, that 2, this 3. So when I connect 1 to 2 to 3, that is clockwise with the lowest priority on the dash. So that is R. So you get a 1R. For the left carbon, again, hydrogen is on the dash, so our lowest priority is on the dash. I have carbon, carbon, carbon. 2 hydrogens and a carbon, 2 hydrogens and a carbon, 2 hydrogens and a carbon. Then I get 2 carbons. Oh, this is tricky. I gotta actually write this out. So this is, I get carbon, carbon, carbon are those. Then it was HHC. And this is HHC, HHC, and then that puts me here. So then that's 2 carbons and a hydrogen. To the right is 2 carbons and a hydrogen. Up is 2 hydrogens. All right, so that's definitely 3 is up. So then, where am I? I get 2 methyls versus let's see, that's that one, versus CH2 carbon. So this is going to be 1, that should be 2. So this is 1, 2, 3, that is clockwise, so that is also R. Cool. Any questions? All right. Is this helpful, going through like this? All right, because I just realized we only have like 2 minutes left. Do you want to keep doing this on Wednesday and just meet again? It'll be optional. I mean, I guess technically every class is optional as to whether or not you show up. But yeah, we can keep going through the rest of this. All right, cool. Yeah. We're still going to keep going today. We still have a couple of minutes, but. So if you're including the 2 R's, then instead of writing that cis, you would have that 1R, 3R, dash 1 ethyl, 3, blah, 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 blah. Yeah, it'd be either or. You wouldn't do both. Cool. All right. So what is we'll interpret our chairs. What is the relationship between these 2 molecules? Start with connectivity. That'll always be an easy, quick filter. Do they have the same connectivity? No, they're automatically constitutional isomers. Actually, I guess start with, do they have the same number of atoms? So I see that it's a chair with a methyl and an alcohol. So I'm like, all right, cool. I know they have the same elements. So I would check different molecules first. Then I check my constitutional isomers, because I'm going to check the elements are the same. Then I check connectivity. Those are really quick, easy, funnel it out. So what I see is I get 1, 2, 3, whereas this is 1, 2, 3, 4. They do not have the same connectivity. They are constitutional isomers. All right. How about the next one to the right? Yeah. What's up? They're not resonance. These are going to be constitutional isomers. They have different connectivity. So what I'm looking for is I see that this is an sp3 hybridized atom. I'm looking for something that is unique. And then I see here is another sp3 hybridized atom. So I have different connectivity. These are constitutional isomers. Cool. All right. It'd probably be beneficial if you want to try to finish this on your own time before next lecture. That way we can do more targeted questions instead of just trying to do all of it straight through. So try to attempt the rest of this and then let me know which ones are your favorite to go over. All right. Have a wonderful day.